experimental data to determine the exponents. We had to look and see the correlation between how much the rate went up per something doubling. So you could imagine, what if something tripled? How would that affect it in the same relationship as doubling? We also found that the coefficients in a balanced chemical equation do not correlate with the exponents, right? That was another important point. What else? We saw that when we looked at taking the rate law and making integrated rate laws based on the order, primarily we looked at the first and second, even though I gave you a summary that had the zero order as well. How you can translate that into a graph, right? A linear graph, and then from that graph, how you can get information to determine things, right? And then we also looked at Arrhenius's equation, Arrhenius's plot for the K and what that equals to, okay? And we were able to adjust that into a linear equation as well and graph it, and then we can get information from that also, right? Things like activation energy and what K is. So with all of that, now we're going to progress in our discussion, and we're going to try to take some of those things and correlate it in newer ways, now that you know that information. We take the information and we build on it. And that's exactly what we're doing at the end of this chapter. We're building on all the information that I just presented. Hopefully I didn't leave anything off. So one of the things we looked at, and remember we talked early on where we saw this chart that said if the rate doubled or if the concentration doubled, what happened to the rate, right? And we had, you could have a negative, right? You could have half. You could have 0, 1, or 2, right? Which are the more common ones. And how could you have half, or where do those things come from? We talked about that it could be more than just one step. And then we did talk at the end, I think, of Tuesday's discussion about how there are multiple steps a lot of times, right? It's not just one step. And we looked at, there's a transition state, right? When we looked at the activation energy. And that transition state, how do you get to that transition state? And we saw something like a wobble and energy being put in, and enough energy put in. Some of them wobble to that top of the activation energy, and then they can come back down to products, and some don't make it on a wobble. But that's just if you're looking at one thing wobbling. There are other things involved, right? You have two different things coming together, something separating, a variety of different types of reactions occur. Okay? And sometimes it takes different steps for that to happen. But when we write it out in a chemical equation, especially through 101 up to this point, all you ever see is just whatever the reactants are and the products. So the assumption is that these turn into these. Not that these do something else, and those something else in combination with different things are what create the actual products. In other words, there was a mechanism that went through multiple steps. And you sort of saw that a little bit in thermochemistry, right? We saw that in Hess's law a little bit. But then once again, the overall equation was something like Na plus O2. So there's 2Na plus O2 gives you 2NaCl, or Cl to 2NaCl. Remember that? That was what we looked at Hess's law in 101 in relationship to that, right? And the breakdown. So you saw that there were multiple steps, but we didn't describe them as literally steps in a pathway based on chemical equations, right? We just said we were looking more at the energetic component of that, where the energy comes from and leaves from. But essentially, if you break that same thing up into steps, those are all the steps that create the mechanism for that total reaction to occur. So it doesn't just go from Na solid, right, plus Cl2 gas to NaCl. It goes through all those individual steps, which of course are energy dependent. And so at that point, we just focus on the energy component. Now I'm saying, now we're going to care about the steps, okay? And that deals with reaction mechanisms. So, and I think I already brought this up, right? Each of the steps in between the total or complete equation are called elementary reactions. We talked about that, right? Okay, good. So we've seen this slide. Did we get, how far did we go here? Did we finish this elementary equations? We already talked about elementary? Oh, good, okay.
Yeah.
Let's go through.
Into the rate law.
We just didn't do the examples. Yeah.
Okay, so we got to the examples, good. This one?
Yeah.
Okay. Okay. So the decomposition of O3 is thought to occur in 2 steps. Oops, okay. So we didn't do this example?
No.
Okay. So this is an interesting example because this is something that you don't necessarily want to happen. And remember, I've talked a lot through this semester so far about how not everything is for a productive thing. Sometimes it's a deconstructive thing and it's not good necessarily. So when we're looking at the decomposition of O3 here, ozone, that is not necessarily a good thing, right? So this is not something we want to speed up. However, knowing that, if we understand how it works, maybe we could find a way to inhibit it. So knowing the mechanism is important in multiple ways, either to speed something up or potentially to slow it down, right? So it's not always a negative thing to understand how something that you don't want to happen happens, because now you have a chance to try to stop it or inhibit it or slow it down. So O3 on its own, this is kind of odd here. Okay. O3 has UV light come in, right? Or just let's say sunlight. That's an energy that comes in and can separate this in a very slow fashion into O2 and O. Start with that. The O there is actually a radical, which is just usually represented by a dot, and that dot then becomes very active, right? It can interact with, wants to interact with everything because it wants to connect. You always want to have paired electrons around it. Having a single electron not paired creates extreme activity, which is exactly where you have problems in your cells when something goes wrong. You have a radical in there destroying DNA, RNA, protein, everything else. So this is actually a radical. Now, then another O3 combined to this radical, and now these two have those shared electrons, which become one O2, and the breakdown of this O3 creates another O2. So the overall reaction here, you're going to have 2 O3s, and you're going to end up with 3 O2s. And if I look, and I'm looking at this carefully, I have this O here and O here, which are actually radicals, right? And they cancel out in the overall equation. They're called reaction intermediates. So you never see them when you actually write the equation for the decomposition of O3 into O2, because this is all you see.
Are they also considered spectator ions?
Okay, so that's interesting. So if you recall, when you do a double replacement reaction, primarily you see this with any of them really, but you usually do the complete equation, the complete ionic equation, and then the net ionic equation, right? And the difference between the complete ionic equation and the net ionic equation are the ions that were not participating in the actual reaction. They literally did not participate in that reaction. These literally are, right?
Yeah.
So they're not, that's a different term because these are playing a role. They're just not seen in either the beginning or the end of the actual reaction. But they were vital to this going from here to here. Whereas what you just described, spectator ions, they have no involvement whatsoever. They're just sitting there in the solution. So that's the distinction. Okay. So the mechanism here is broken up into 2 steps, and each step on its own is called an elementary step or elementary reaction. Okay, that makes sense? Okay. Sodium bicarbonate, I want to add one other thing. I want to add it here. One of these steps is going to occur faster than the other, right? That would be called the rate limiting step. That's a hugely important step to be able to identify in this, okay? And remind me if I don't say it, because I don't think it's in your notes, how I personally would correlate that rate limiting step to the things you've learned already, like the rate law. Because there's a direct correlation between the rate limiting step and the rate law, which is exactly why you have to do it experimentally to determine the exponents. Okay. So sodium bicarbonate can be synthesized through what they say are 3 elementary steps. Here are the 3 steps. CO2 plus H2O forms carbonic acid. In Chem 101, what would that mean to you? What is that called? What is carbonic acid? Unstable.
Unstable intermediate.
Yes, thank you. So it would quickly degrade into what? H2O and CO2.
Okay.
Right, we're going to keep it together because before it has a chance to do that, in case you were worried, it binds to, oh, look at that, another unstable intermediate, right? Ammonium hydroxide, which turns into what? Ammonia and H2O, if it was on its own. So I have these 2 things now. They're going to interact with each other, and they're going to basically do what? A double replacement. NH4 is going to bind bicarbonate, HCO3, and that leaves me with the OH and 1H here to form the H2O. That's just simply a double replacement reaction that you guys are all familiar with. In fact, isn't that an acid-base reaction?
Right.
There's your H2O, this is the base, this is the acid. So sometimes you can identify certain things that are going on, even though that wasn't the intent of the slide. Now I have these 2 things, right? Then this thing here is going to come over here. It's going to mix with sodium chloride. It's going to do another what? Double replacement. I'm going to get sodium bicarbonate, and I'm going to get ammonium chloride. So this is sodium bicarbonate that's being synthesized. So what am I trying to synthesize here? This. But I didn't just go from whatever you would see as the overall equation, because now do I have any intermediate reactants here?
Yeah.
Yeah. I have this carbonic acid, right? That's going to cancel itself out.
And the NH.
What else do I have?
NH4Cl.
The H2O, that cancels itself out. I heard something else.
Oh yeah, the
This one,
NH4CO3.
NH4Cl's over here.
No, NH4HCO3.
This one and this one will cancel out?
Yeah.
Absolutely. They're all my intermediates. How about
What is that one called?
Which one?
The last one?
This?
Yeah.
Ammonium?
Ammonium.
Bicarbonate.
Ammonium bicarbonate.
So just the ammonia was the last reaction intermediate, the NH4? You said?
There's no first or second, I wouldn't organize, they're just, the number of intermediates are 3.
Right.
The 3 of them are H2O, bicarbonate, or carbonic acid, and ammonium bicarbonate. Those are the 3 reaction intermediates.
How do you determine which one is the determinant step?
We'll get to that.
Okay.
You'll either be given slow step, fast step, something, and we'll talk more about that.
Okay.
Or alternatively, how would you determine it? Experiment. Experiment. So let's, while you're thinking about this question, probably others are too. So these are elementary reactions. If I said that this was the rate limiting step here, then what would my rate law look like?
It would be equal to that.
It would be that.
Yeah.
And now the coefficient is the exponent. That makes sense? The coefficients are the exponents now. However, I still cannot have a reaction intermediate in my rate law, so I'd have to be able to manipulate that. And we'll look, that's exactly where we're moving towards. But does that kind of bring things together a little bit?
Yeah.
So when you have multiple different intermediate reactions or elementary reactions, in other words, a mechanism beyond what that original overall equation is, then that's why the coefficients don't correlate directly to the exponents in a rate law. But when you do break down the mechanism into the elementary reactions, the steps, then whatever one is the rate limiting, that one now you can take the coefficient and correlate to the order, as we called it, or the exponent.
Is that something that you would ask us to do, or just simply to understand that that does
You're gonna have
happen?
to do that. We're not there yet. I'm kind of
Yeah.
prepping you since that came up now to kind of phrase what's happening here and frame it appropriately. But now we're gonna do some problems and we're gonna get into more of that. Okay. But since it came up here, that was a good way to start like introducing that topic, which is a really important one in terms of why we're doing this and why we did all the things we did up to now, by the way, right? So a lot of times there's a disconnect as you go through and you're like, well, the rate law is the rate law. That has nothing to do with mechanisms. Absolutely it does. And I'm trying to bring those things together. Okay, so here, what is gonna be my overall reaction? Those two. There we go. So from here, if I wrote the rate law, the exponents cannot be the coefficient because it's going to be different than the rate limiting step. And in this thing, this is the kind of thing you've seen up to now, where you don't see all these steps. So this looks like that's all that's happening when all these other things are actually occurring in order to get there. How do I know this is the right mechanism? Experiments. What do I mean by that, though? When I say experiment, what does that mean? We talked about experimental data earlier. The very first time we talked about it, what did that allow us to do? Determine what? The exponents. So if I do experiments, I figure out the exponents, then I match them to the proper rate limiting step in the mechanism. That's also how I know which mechanism is correct. So they all correlate. That's going to correlate to the proper rate limiting step. Because if I have a step that's really fast, this is really, really fast, I'll make a whole bunch of this. But this is really slow, then it doesn't matter how fast that is. And then this one's really, really fast. These two are irrelevant. It's whatever this one is, that's the rate that this reaction will move. So the rate limiting step determines the rate law because that's based on the rate and the reactants. Is that sort of coming together a little bit? Okay, cool. Let's see what happens now. Okay, quick diversion before we get back on track to what we're doing there. This is just called molecularity. These are just really a system to determine, a system to state something. So other than the actual nomenclature here, it's not that big of a deal. Unimolecular reactions, elementary reactions that involve one reactant. No big deal. Okay, nothing major, no new intellectual idea here. So you have something like a decomposition. Generally, if you have a decomposition, they're going to say it's relatively unstable. That's why it decomposes. But that's not always the case. Here they're stating it's unstable, which kind of implies that it does this pretty easily, which it doesn't. In addition, it needs light energy to go in to do this. It's not like it's just going to sit around and do this, but they're claiming it's unstable because most decompositions are generally a little bit unstable. That's just one thing. So the main thing here, unimolecular, this is an elementary reaction, and it has only one reactant. That's it. It's that simple. So once again, this is only if it's excited and unstable under certain conditions. Okay? Under its natural conditions, it's not that unstable. Bimolecular, what's that mean? So you guys can tell me what that means. If unimolecular meant one reactant in an elementary reaction, what is bimolecular? Two reactants, that's it. In an element, but make sure though, this is in an elementary reaction, not in an overall equation. So keep that in mind. That is the one thing that you gotta be aware of. But other than that, that's it. Okay. 1, 2, some rearrangement, I get something else. What is termolecular? 3, that's it. Like I said, no big deal, nothing highly intellectual here, just a way to define things. Okay. Whoops. And they didn't even give me an example here. So you have 1, 2, 3. Is this going to be common? No. Why not? Just from your knowledge. Why would and you've seen this, decomposition. Oh, okay, let's go back to Chem 101. You have synthesis or combination. That's one type of chemical reaction, as we learned four or five of them, I think. Then we went to decomposition, which is the opposite of the synthesis. Single replacement, combustion. Those four were all redox, right? Exchange of electrons. And then the fifth one was double replacement, which is not a redox, no exchange of electrons, and there are three types under that, right? Everybody remember this, hopefully? Gas producing, neutralization, and precipitation, right? Okay. How many of those in any of those reactions we just talked about have three reactants?
No.
None of them. Okay. So you can see that this is less common. But why would it be less common, thinking of what you learned from 101 that we just discussed to what you've already learned this semester? Why would that not be so common?
Increasing randomness?
Because of the interactions and the orientation of those interactions, absolutely.
Would you say that is increasing randomness? Like, you could actually come up to anything else now there's more differences?
Proper orientation.
And the proper
Things
right.
have to bind. Remember, we just went through that proper orientation thing? Where was that wrapped up in? In the rate?
Yeah.
K. What did we call that section of K? A, and it was broken up into P and Z, but what was the A called?
Frequency.
Mhm. See this review, it's nice but you can also see now how easy it is to listen to me up here.
Frequency vector.
What is it?
Frequency.
Frequency. And then what was the other part?
The
So-
collision frequency.
The orientation factor or exponential factor, we called that, and then we had the frequency factor, right? So you could see that there's always going to be some studying to do prior to the exam because it seems a lot easier, but then when I bring up something that we learned, on Tuesday, 2 days ago?
Yeah.
It's easy not to remember certain things, right? So we got to be a little careful on interpreting information in here when I'm talking, and then when you're on your own, being able to do that so that you're prepared for the exam. For those of you that take me, you know I say that. Hopefully at this point you realize what I mean by that, right? Okay, because for whatever reason, I hear all the time, it seems really easy when I'm up here and I'm working with you guys, but I'm guiding you through this, don't forget. I'm also taking you in very set sequence of things, information, because it builds on itself. In the exam, they're all juxtaposed, and you have to figure out the correlations and how they work. Okay, and of course, you don't have my face sitting on your shoulder telling you do this, do that. I would if I could, but then I couldn't assess you, right? No reason to have the exam. Okay, so intermolecular, these are less likely because of all the things coming together in the right orientation. Which is why you didn't see them as much in 101, because it's more complicated, therefore we don't want to talk about anything too complicated at that level. Okay, so this, all right, maybe we should skip this slide. What is the molecularity of this? Sure. Hopefully that's how they give another one. I. This is way too easy for this level. Uni, okay. Okay, just so you know, uni, bi, ter, molecular, based on the number of reactants in a very specifically elementary reaction. That's it. So of course I could ask a simple multiple question related to those things. Okay, moving on to something more relevant and the things we were talking about prior to that. That's just, nomenclature stuff. This is exactly what I just got done saying, right? For the overall reaction, the rate law cannot be predicted. Okay. The rate law. Where can it be predicted based on what I already said? From an elementary reaction, which one?
The slowest.
The slowest one, or the rate determining one. Okay. That pretty much is everything that's going to say here, except for the way I just stated it is probably a much more clear way to correlate everything. Okay, so now we're going to look at these elementary reactions using molecularity as a term here for uni. And we're going to see what the rates are for these kinds of things. So we're correlating the rates related to the elementary reaction here. Okay. No big deal. You guys already know that now based on our earlier discussion today, hopefully. I'm just now putting them into these terms. Now, my assumption, though, is that these are going to be rate limiting steps when I'm looking at these elementary reactions. Okay. So, I think we can skip this. You guys can figure this out, right? What would the rate equation for this be? Let's just do one. If there's more than one, we'll skip it. K, concentration of O3 times the concentration of NO. Yeah, that's it. Let's do this one. This is now applying what I mentioned earlier. So the first thing I want to do, now here's something important, and can be easily overlooked. The very first thing is what kind of reactions am I looking at?
Composition.
Not types of reactions in that format. I'm looking at the mechanism here. So am I looking at the overall equation with this, or am I looking at what? What is it telling me up here?
Elementary.
That's very important. If I'm looking at the elementary reaction, then I could write the rate law for it.
Okay.
I can't do that with the overall. See that subtle distinction? Understanding that you're looking at elementary reactions, which are all part of making up an overall reaction, allows me to put the rate law for that elementary reaction in the context of the exponent being the coefficient. So what's my rate law for this elementary reaction? K, concentration of NO2 to the power of 2. Absolutely. Because it's an elementary reaction, now the coefficient matches the exponent. Remember I mentioned that, but now when I actually ask to apply it, it's a little different. Have to know it's an elementary reaction though, otherwise you can't do that. So, looking at the suggested mechanism for a particular reaction, I could make all kinds of suggestions I want. I could come up with multiple different mechanisms, but only one is likely to be right, and that one, if it's right, experimentally will match the rate law of the elementary reaction. Okay, does that make sense? Okay. If I come up with a better one that also can do that, then I have to figure out which one is actually happening. But I still have to do this experimentally to figure out. So if I do it experimentally, that just means that I'm solving for the exponent and I figure out my rate law. Then I have to match the different mechanisms. One of the elementary reactions has to match that rate law. Right? So that's how I'm doing it. I'm still doing it experimentally the same way as before. However, that does allow me to say, though, if I already know what the elementary reaction is, I could then figure out the rate law from that, right? As opposed to going from the rate law to the elementary reaction, which is what I do experimentally. Let's see. Okay, so this is sort of what I was saying here. The suggested mechanism is considered correct if it agrees with the experimentally determined rate law. Okay, obviously. And it's not if it doesn't. No different than what I already said, but this is, if you're studying, you're going through, this has these nice little areas that are highlighted that help you. It's really the first and second, they kind of mean the same thing, obviously. So let's do something. Okay, my overall equation here. 2 NO2s plus F2 gives me 2 NO2F. So here, my rate is what? What's my rate here equal to?
K, NO2.
K, NO2 to some exponent, and F2 to some exponent. That's all I know. That's all I could write from this.
All right.
I don't have any data. If I had data, I could fill in what the exponents are for the NO2 and the F2. What if I told you this was the elementary reaction, one of them, in the overall mechanism, and this was the rate limiting one? Then what would I write for the rate? Absolutely. I heard that right in multiple different ways. K, concentration of NO2 to the second, concentration of F2.
Yes.
Okay, no big deal. But for now, all I know is this is the overall equation, not the elementary equation. Therefore, I cannot write it that way. I can only write with the exponents as n and m, or x and y, or whatever you want to put. They're unknown. You don't know them yet. One suggestion for the experimental, oh, this is the experimental rate law. Okay. And they should have the n and x here. N, m, those are unknown at this point. Well, let me rephrase this. Okay, what they're saying here is not what I just said. They're actually telling you this is the experimental rate law.
Yeah.
Okay. This is the rate for this reaction. That's why they don't have the n and the m here. They're saying they're 1 and 1. In other words, from their data, which they're not showing you, they were able to determine, the same way you guys were able to determine, you held F2 constant. When I double NO2, the rate did what to get 1? Double.
Right.
Okay? That's what they're not showing you here. First order, second order. So you already know this now from your data. Okay. So now you suggest some mechanisms. And say, well, which mechanism? You know that this isn't straight, right? Because otherwise it would be, you would have a square here, or you'd have a 2 there, right?
Mhm.
So there are 2 possible mechanisms that were suggested for this reaction. The first one is this. NO2 plus NO2 plus F2 gives me 2NO2F, which is kind of the same thing as what they just showed pretty much. Right? And that wouldn't work because the predicted rate law is this. In other words, they didn't do anything there other than separate the coefficient in front of the NO2. They just put 2 there instead of the 2 in front of one of them. They're saying it's a straight mechanism. The mechanism is it just goes straight that way. But you know that's wrong because it has the 2 here, and that doesn't match what the actual experimental data indicated as the rate law, which where this was just 1 and this is 1.
Right.
So then can this mechanism be right?
No.
No. You eliminate it. And that's what those boxes were saying before, right, that I pointed out. So you're just deducing that from what I know experimentally, this mechanism cannot be right. Okay, no big deal, right? So my next mechanism for this is this. It's in 2 steps. I have this, and this is my constant for this reaction, and this is my constant for this reaction.
Okay.
This is my slow step, this is my fast step. 2 steps. Each one of these are what? What do I call each one of these equations? Elementary.
Right.
Hugely important here, right? Because that implies that if this is right, one of these elementary reactions is going to match the actual rate law.
From the experiment, right.
But which one would that have to be? The slow step.
Right.
I want to also recognize something else here. This is a single arrow both ways. That means that this goes all to here, and then the NO2 mixes with this F here, and it goes all the way to there. And there's a rate constant for each. Okay, so far? So my rate limiting step is my slow step. In other words, this is where the bottleneck occurs, right?
Yeah.
I have a bottle, I'm pouring sand into it, and I could pour as much as I want, it will just fall off the side because it still has to go through that little bottleneck before it opens up into the bigger part of the bottle.
Yeah.
Bottleneck. So this one will dictate this one because as much as I could produce here, I could produce much more of this and all of it will be used up immediately.
Yeah.
So my rate determining step is this one.
Okay.
So then if I look at that step, what is the rate law for that elementary reaction?
Right.
What is it?
The KNO2 and then F2.
K, NO2 to the first power.
Right.
And
F2 to the first power, does that match the experimental data's rate law?
Yes.
Yes, that means that this is likely, that at least between those 2, this one is the mechanism. Does that mean that I can't find another mechanism that does this, that may be more efficient?
You can.
Yes, that's possible. So we could potentially get something better, but at least for what we know and we can come up with, this would then be the proper mechanism for that particular reaction.
Right.
Okay, everybody see that? And you can see where the intermediates are here, that the F and F cancel, that's why you don't see them in the overall equation. And that matches. That matches the experimental data, which is a good thing, right? Because now I'm pretty comfortable that's my mechanism. At least from what I've proposed, that's got to be the mechanism. Does that make sense? Everybody see the correlation and how these things are working? Yeah? Okay, I think we probably have another one. Let's see. Which is first order, second order, and therefore predicted rate law agrees with experimental rate law. Mechanism, not bad terminology, is likely is a better way to state those kinds of things. So the mechanism must be correct, is likely correct. Okay. Okay, well, here we're back to the decomposition of oxygen. So the following mechanism has been proposed for the decomposition. So now we're just simply showing a mechanism here. Okay, so last one we gave you some information first. Now we're looking at the mechanism itself. Okay. Here's the proposed mechanism. What's different about this mechanism compared to the last example I gave?
It has a equilibrium.
So two things. One is all the arrows don't go directly through. So this is forming an equilibrium, which is the whole foundation for the next 3 chapters, right? Let me just quickly recall for you what that means. I have something, it goes one way. As it goes this way, it starts to slow down and some of it starts to come back. When the rates of them going this way and this way are equal to each other, then you are at that equilibrium. Not that you have more here or less here, or the same or anything else. It has nothing to do with the amounts. It's just the rate of this converting into here and this converting back into there is the same. So at any given time, there's no movement in the amounts on each side, even though they're not necessarily equal. In fact, they usually are not equal.
Got it.
Does that make sense? Now that we know rates, that probably makes more sense than when I said it in 101. So that's an equilibrium. So I have a k going this way, and a k1, and a k to the -1 going this way. And those should equal each other. Those rates should equal each other. Not the amounts. That's hugely important. It also means when you orientate yourself, this is the reactant with this one. These are the reactants with this one. Okay? Now that's a different way. You've got to see it that way. Okay, now, it's a fast equilibrium. So that means this turns into this, but this just as quickly turns back into that. Now, this, there's plenty of this, right? Ozone, so this is happening. And then a side reaction, another O3 comes, and it could grab that O, and then through a different rate, turn into this. And this is a much slower process. So that makes this the rate determining step. Okay. So in this rate, so then, and let's say we know this. This is a given. I'm telling you this. Okay. So then what does that mean? What is the rate of this overall ozone being broken down into O2?
Okay. KO3. Oh,
K, concentration of O3 times the concentration of O.
right.
Oh, so the O's don't.
What's the overall equation, though?
Doesn't the O3 cancel out?
203 plus 202. So is it-
Yeah, O3 equals.
O3 to 202.
Those are react.
Three
But
of two.
I also told you that was what? A radical? Just to keep that in mind, just for your own personal knowledge. This is kind of a simplistic version of it.
It's 203.
Oh, whoops. It's not showing.
203.
So
I think it's the next slide.
this is the rate determining step. Is this an elementary reaction? Yes. So then can I take this as my rate law? What's the caveat there?
It's possible rate law.
Why can I not use, let me write this on the board to make this clear what this is. So the rate
It's the predicted.
is going to, and the rate, this is really the rate of, and we don't usually see this, but I like to think of it this way, so I'll write it this way to help your thought process. This is really the rate of the degradation or the decomposition, let's say, of O3.
Okay.
That's what we're really looking at. That's what we're about. You got to put this in context, right? What are we evaluating?
Right.
Yeah.
Okay, so this is the rate. And the rate of this, based on this mechanism, presuming it's correct, which I'm telling you it is going to be K, concentration of O3. Of course, this one doesn't work, right? Times the concentration of O. The overall reaction here is O3 goes to O2, and there are 3 of those and 2 of those.
Right.
What's odd about this rate when you think about the overall equation?
It doesn't have an O in
The
it.
exponent?
It's plain exponent.
Yes, the reaction intermediate is in here, but where is it over here?
Okay.
So you can't have it there. So I have to look for some way to make this into the equivalent of something that's in here.
1/2 O2.
Zero power?
Hmm.
Wait,
But it's, you already know it's to the 1 power.
Can you say O2 to the half?
This is, right, based on this, I'm saying this is the rate limiting step, this is the mechanism.
Yeah.
So therefore the rate is this, it is 1 and 1.
Yeah. But you need to make it equivalent.
Would it be possible to find the rate of the first one and then isolate for a concentration of O and then plug it in?
It's exactly what you want to do.
Oh,
You want to fix this here and make it equal to something that allows you to match the overall equation. The one thing I can do, remember the first example I couldn't do this because I didn't have an equilibrium, but I have an equilibrium here. The rate of one direction is equal to the rate of the other. Meaning that the rate of K1 concentration of O3 should be equal to the rate of K minus 1 times the concentration of O2 times the concentration of O. Then I could isolate O. Absolutely. So let's take a look at, that's what comes up on the screen next, I think. So I take this, there's my slow step, so my rate, so they're just now redoing what we did here. Okay, but reaction intermediate cannot be in the rate equation, in case you didn't catch that part. It's in capital.
K2 is just for the example too?
What's that?
The K2 is just for the example too?
What's the rate in that one? My
Okay,
rate law is
okay,
based
okay.
on the elementary equation,
Right.
absolutely.
Yes. That's right.
Okay. So now what I do know now, okay, is that as I just mentioned, I have this equilibrium. So I can say, so I can set the rate going this way equal to the rate going this way. So the rates are found in the rate laws. So the rate equals 1, and that should equal the other. The rate's the same in both. That's what the equilibrium is. That's what I meant by rate. It's also, I should just add this one term, dynamic. That means that they're actually going both directions, just at an equal pace, an equal rate. Dynamic meaning that they're not static. They're actually going both directions. Okay, so, oops. Rate forward equals the rate back. So the rate for the forward one is K1, O3, and this one is going to be K minus 1, O2, O. Everybody okay with that? Is that okay so far? Now, what am I trying to do? I'm trying to replace this. So that means in this, I want to solve for this. So if I take these two things and I divide it down, this equals K1 concentration of O3 divided by K to the minus 1 concentration of O2. Is that okay? Now I can simply take this and plug it right into there. In our example here, that would plug in right into here. Now, what do I have? O3 and O2, are those part of my overall equation?
Yes.
Yes.
Then you have 3 different Ks.
Which each one is called, sorry, yes.
Okay.
And what is a K?
It's the temperature. Yes.
Forget about the components of each K. When I call it K, what am I saying?
Constant.
It's constant, which means what? Does it change?
No.
No, if I take 3 constants, it's now what? 1 big constant.
Right.
And you-
Right? That's, why not? What?
Yeah,
So I'll take all
some
3. I'll take K, this is K2 here. I'll take K2 plus times K1 divided by K to the minus 1 and just call it all 1 constant. It's still a constant.
Exactly.
Is that okay?
Yeah.
That makes sense? So that eliminates that issue.
Uh-huh.
Okay. So let's see here. So I'm going to substitute in there just as I said. So now I have all of this in here. Remember, I have the K2 and the O3 here.
Mm-hmm.
If from the original. I now have just plugged in the K1 and the K to the minus 1 and another O3 and O2. So there, O3 and O3 is just O to the second. There's two of them.
Can we just try to 1K instead of all three?
I'm going to wrap that up all into one. Absolutely. I could have it written like that or combine them all.
And doesn't K1 and K negative 1 cancel each other out anyway?
They're different
Or they're
rates.
the same?
Or different.
They have the same rate. But, so, okay, just to answer that question, I'm going to lay this out so you can see this. K1, concentration of O3, right,
Yeah.
is equal to K to the minus 1, concentration of, what was it, O2, O, right?
Oh,
If this equals, the rates equal,
yeah, but not the actual K.
yeah, now you can see that. Unless this happens to equal
Yeah.
those, then this would. But as I said, the concentrations do not equal each other.
Okay, gotcha.
That make sense?
Yes.
So it'll always just be like 1K.
Yep. You just call it 1K.
Cool.
Wrap it all up in 1K, and now I have this. Now this is interesting. Right? Now this works. This is the actual rate of it.
And it turns into O2.
So what is the order of the O3?
2.
Second order.
Wait, second.
And what about the O2?
1.
Negative
Or
1. There's your
negative one.
there's a negative, right?
Right.
Right. So this is your overall rate for O3 degradation or decomposition.
So would the overall order be 1?
The overall order would be 1.
All right.
But then again, do we care about the overall order? Not necessarily. That doesn't really play
It's
much
just like
role.
a
Yeah.
estimate.
Why was it -1 order of O2?
On the bottom? You know?
So 1 over this, right,
Oh, okay.
is the same thing as
Okay.
that.
So does it just like cancel? Because you can't have a negative order, right?
No, you
Can.
You can?
If you double the concentration, what do you get in terms of the rate in order to get a negative 1? What happens to the rate?
Slows down.
Half. Yeah. You see how it all correlates, which is exactly what I'm trying to do. I'm correlating all the things you learned earlier to now so that you don't get lost. So I don't want to make this segmented so that each part exists on its own. I want to bring you along and keep building, but they all relate to each other. Okay? Ideally, that's what I'm doing, if I'm doing my job. I guess I'll see on the exam. That's why I always want you to do well, right? Not only does it mean you were interested and learned, but it means I did something right. Go ahead, Peter.
So if it's a negative order, would that mean that it's like more favorable to form that?
No, it just depends on what the rate happens. It's based off the mechanism, right? The mechanism were those two different spots. So whatever's happening in the slow step to the fast step to how many different things are going on, that's what matters. That's going to dictate the overall rate of the reaction. And that's all we're correlating when we talk about these orders. We're just talking about the correlation between adding more reactant and getting some rate associated with it. Does it speed it up? Does it slow it down? How much does it speed it up? Everything else. And then where would it fit in the overall rate order so that I could determine things like K or the rate. Can I figure out K?
Yeah.
Yes.
At this point, yes, if I have certain information, I can figure out K, right? Can I figure out the concentrations here?
Right.
Then I can figure out the rate. If I know the rate and the concentrations here, I can figure out K. If I know K, I can figure out activation energy. If I know activation energy, I can figure out how to lower the activation energy or something like that, right? It's all intermingled to figure out the different things or the dynamics going on for a chemical reaction in terms of the speed it takes. That's what kinetics is. Okay. Now, that knowledge, and yes, you will have a problem like that on the exam, just to let you know that. I like to let you know certain things that are more challenging problems that I will ask that question, so learn it. Got plenty of time. For whatever reason, even though I say that, I'll still only get about 60% that get it right. I'll still get 40% that don't get it right. Somehow you don't believe me. But those of you who have taken me know that I do that, right?
Right.
I will. If I say it, I will. In fact, I've even done a problem on the board that I thought was challenging prior to an exam. right prior to, during the exam time, just before it, left it on the board, it was the same thing that was on the paper, and still only 40% got it right. So sometimes it doesn't matter what I do. I did that just to see if it was me or if it was just that it's how you guys are thinking, not me. Like I got to assess that too, right? Am I doing something wrong? I'm just not able to articulate what I'm trying to say clearly, or whatever else. So when I do say those things, it is because that's what I think is important for you to know. Those are the more challenging things I think you should know it, and in order to move on to the next level, because where are you going after this? OChem. And you need to have certain skills and know how to do certain things at this level to do the OChem. Those who are not moving on, still good to know. You still learn something, which is always a powerful thing. It allows you to figure other things out, and it makes you more competent in many areas because you can cross over multiple different disciplines, right? Ideally, and nowadays, you want to cross knowledge, your own thinking ability into things happening in politics, right? That's always a good thing to be able to do, assess that yourself. Don't just listen to what somebody else is saying from their perspective and their angle.
Right.
And being able to think properly through things like this helps you think properly through other things like that. So keep those things in mind. It crosses over disciplines. Okay, so catalysis. This is pretty straightforward, at least the term. But I'm going to break it down into a little bit more, make it a little bit more complex into what's actually happening when we use the term catalysts. So we have something, let's say x plus y goes this way, and then we have a plus b. Okay, and we just talked about rate, so let's say there's a rate assumption with k here. So this could be favorable or unfavorable. It could lead to something positive that you want to happen or something negative that you don't want to happen. Let's take it in the context that we want this to turn into this. Okay, and so I have a rate constant, and let's say my rate of this is 1 times 10 to the minus 80. Is it fast or slow?
Slow.
It's extremely slow, but I want it to happen,
Yeah.
right? And I'm saying, okay, maybe I don't want it to happen most of the time, right? So let's say you have cells in your body and you have certain things that you don't want to be turned on, certain transcripts that you don't want to make.
Yeah.
Then all of a sudden you get something that happens in your body, and now you need to defend against that something. So you get external signals that hit a receptor on the cell, which then create a pathway, a transduction pathway, which then gets into the nucleus and turns on the gene-making apparatus to make the protein, enzyme, or whatever you need to beat it. And this is that process. So 99.9% of the time, I don't want this to happen, and that's why it only happens at this amount. Now, I want it to happen. A couple things happen, transcripts are made, and I find a catalyst. Okay. Catalyst now changes this rate, speeds it up, and now my new rate, let's say, is 10.
A lot faster.
So it's now moving faster. What am I doing? I'm making a whole lot more of A and B because I need B to kick out some antigen that is clogging up some pathway that allows my cells to function appropriately. So I could do multiple things as a cell, right? I could go through apoptosis and try to break. I could make this, and this could maybe kill off those cells.
Yeah.
Or I could make something that just blocks this thing that's in here or takes it on its own, kicks it out of the cell. There are a variety of different things that this protein, let's say, may want to do. But the key is I want to get that thing out of there. In order to do that, if I sat around waiting for this, I'll be dead in, say, 5 days. My cells will proactively say, wait, we're not going to let that happen because we're surviving. We're going to do this. We're going to make some of this from an external signal from the cell. This is a big cell, right? And there's my receptor. An external signal that makes more of this thing, which catalyzes it and speeds this up. So I get a bunch of this thing, which can now restore the use of my cells, or at the very least, kill them off so that they don't affect adjacent cells. So it doesn't keep happening.
That's how the
That makes sense?
vaccines. The vaccines are made like that then.
Yes.
Okay.
Some are, so you have a certain amount, and then you make more depending on external signals. Absolutely. It's exactly how the whole body's functioning, right? So in this example now, I want to increase this rate. I increase it with what I call a catalyst. What a catalyst presumably does is it brings together X and Y, makes them closer so that they can interact appropriately. In other terms, what does that do to the K? It decreases the what?
Activation.
Activation energy, right? And how does it do that? It brings them together through proper orientation. Now you see where all these things are working, right? That's what increases the K. K goes up. This becomes K, let's call it up. Super K. And now we have a faster rate and our cells are safe. At the very least, our tissues are safe from the bad cells. Okay? As just a general practical example of why we would or wouldn't want something. In this case, this is why we would want something. You can clearly see in the ozone case, maybe we want to find something to prevent that, right? So there are a couple different, or if I have a cancerous cell that I have something constitutively active that's ubiquitous throughout, I might now want to take something to block that, right? Which is what most of the research is done on, either blocking it or killing off the cells.
Right.
So you could want this, or maybe you want to, maybe it's already at a rate of, say, 1 times 10 to the 80th, and I want to bring it down to 10. So it could go either way. It all depends on what it is you're looking at, evaluating, and what matters in each situation. But anyways, a catalyst is going to speed up the reaction, but it's not actually used in the reaction. Because catalyst is made now, sits like this, substrate comes in, it adjusts. So now I have, what do I have? What is this called? Transition state. This is my ES together with the catalyst. And then it brings them in, proper orientation for the ligands, and they form. Now the catalyst opens up, this leaves, and the catalyst is presumably back to whatever it started with, but you now have a new product.
Active site.
And that would be inside the active site of the enzyme, yes.
Right.
Does that make sense? So that's what a catalyst can do, but it doesn't have to be an enzyme. That's just for a biological system. Okay? So it's anything that's going to speed up that reaction. And usually not used, even though there could be side reactions that happen where some of it is used up or pulled away from the main reaction. That's also possible. So then in a cell, if you're looking at an enzyme, and let's say you have an enzyme that's got a rate increased too much, what would you try to do to it?
Denature, yeah.
You'd try to, but well, so now if I'm trying to denature an enzyme in a cell, how do I target just that enzyme to denature it? Usually you denature things with like temperature and stuff, right?
Right.
That's going to harm everything in the cell.
Exactly.
So that might not be the best strategy, right? Because unless I want to kill off the cell, but then I could also kill off the cells next to it and the ones next to that.
Substrate than the enzyme? The more of it?
So what if I know if I have the enzyme, I have an active site, I have 2 ligands coming in there that are now coming back out too quickly and forming a product. What can I do? Inhibitor, what does that mean? What would I design? Wouldn't I design something like one of the substrates or both substrates that will also fit appropriately? Could be allosterically, into the enzyme, and then block it.
Right.
But I don't want to block all of them because I need some of it. So I got to find the proper concentrations and the thing that's going to sit there, but also maybe I don't want it to sit there forever, so something that will sit there for a temporary period of time, so it's stable but not too stable. Otherwise, if it locks it up completely and they lock all of them up, now I have no enzyme to do anything in that context, whatever it is I'm trying to do. So this is how you think about science in general, and when you take these ideas, this is how you apply them. Right? I'm giving you a lot of bio examples because I'm more of a biochemist, because to me that's more relevant, what's happening in my body versus something that's happening in the dirt outside. It's still relevant, we still need to know it, just not as interesting to me.
Right.
So I'm going to give you more practical examples of what I like. So for those who are not bio, hopefully you're okay with that. Okay, so here, this just tells you all these other things we just talked about. Speeds up the reaction without being consumed. Once again, you could have side reactions that it's doing other things with or whatever else. But or if I have an inhibitor that consumes some of it, but not necessarily from the reaction itself. They actually mentioned that side reactions. No, nothing that big, but some of it can be consumed through that process, through some other process. Mechanism. Okay. So that's an interesting statement here, right? This one. So let's go back to the O3 decomposition that we looked at. And we saw O3 with UV light breaks down into O2 and O, radical, right? And that was in a fast equilibrium, okay? And then the next step was that O radical binds or interacts with another O3 and forms two O2s.
When it's low.
And that was the slow rate limiting step.
Right.
Which one would I want, if I want to speed that up for some crazy reason, which one would I want to create a catalyst for?
K2?
The second step, the rate limiting step, right?
Hmm.
Who cares if I speed up the other step? It's irrelevant.
Still gonna be limited.
So keep that in mind, why the rate limiting step is so important, including in catalysis. So if it was bottleneck there, maybe if I just took it and put it in a different bottle that had a bigger neck, then it would speed it up, right? So you can think of it as that simple. I think that your book probably uses something I think I've seen before, don't recall. But this book maybe uses something like a traffic jam or something. So you're on the freeway and you have 8 lanes or 5 lanes or whatever is moving, and all of a sudden like 3 lanes get blocked. Creates a bottleneck there. So after that bottleneck, it moves really fast again, right? But up to that point, everything slows down. So if I could find a mechanism to move all those cars to the side to speed that spot up, then that's where so that would be where the catalyst is inserted, just to put that in context. Okay, so that's why here we're talking about the rate determining step, rate limiting step. Okay, where are we at now? Oh, that's a weird progression. Okay. So in this case, so here's that oxygen breakdown thing. This is a really weird way to represent it. Oh, this is just, they're just showing you the rate limiting step there, that's why. Okay, so in the rate limiting step there, they're saying that this reacts fairly slow. So what speeds this up? Catalyst. Now I've talked about it in the context of enzymes, but this clearly, I don't have enzymes in the air running around grabbing O3s and O's together. What kinds of things are speeding up the degradation of ozone? This is just common knowledge.
Carbon emissions.
Carbon emissions, CFCs,
Chlorine, CF.
greenhouse effect, all those things, right, that we hear about. So what actually is doing that? And is that thing considered an enzyme, a catalyst?
Yes, the chlorine.
Chlorines, CO2s do that, right? So those are usually found in CFCs, and they go up into the atmosphere, and the CLs break apart, and as they break apart, what happens? They speed this up. How do they speed it up? One binds to one, separates this a little easier, or combines to this, which creates more overall O2 from the O3. That's a catalyst. Not an enzyme, that's just a catalyst, something that's speeding up this reaction. How is it doing that? From the context of how we've described rates, where in the rate can a catalyst have the greatest effect?
On this list, the rate limiting step.
In that step, but where in the rate itself? So when we're talking about rate laws, is it actually having an effect? What's happening?
In the elementary.
Frequency?
It's in the rate law.
Right.
What is the rate law? Equal to constant. What's in the constant?
Oh, the frequency, the...
Activation energy. It's lowering the activation energy. So now, if you think of it in terms of that wobble,
Right.
if it wobble, a whole bunch of them, and then they finally get to that high activation energy, then they can come down. What if that activation energy is down here? Much more of them can jump over it.
Yeah.
You're reducing the activation energy, generally. Or in addition, you could be properly orienting them, right? So there are a few different things, but usually it's the activation energy that you're lowering as a result of that. So that's the foundation of a catalyst. It speeds up the reaction in that format. Okay, good. Here's your energy, your reactants, your products. So the first thing I'll point out is you do notice that from the reactants to the products, is that an endothermic or exothermic reaction?
Exothermic.
Exothermic. So you might think of it as probably favorable. I can tell you that not all exothermic reactions are favorable, right? Even though that's the instinct. Maybe there's a different way to state that we'll learn a little bit later. I think this is 101. We'll learn it later this semester in this class. And that's called spontaneity. And we'll deal with Gibbs free energy and all that kind of stuff a lot, probably towards the end of the semester. So this is not necessarily spontaneous. In other words, you can't just put them together and they happen, right? Which a lot of times, if you have an exothermic reaction, which is favorable, you would think that would automatically be the case. But you have to deal with things like other things associated with it.
It depends on the system you're talking
You
about?
need entropy and stuff like that that you have to
Right.
deal with that we're not accounting for here. This is just energy. So here's my normal transition state in my uncatalyzed pathway, and I need to get all the way up to here, so I need that amount of energy to get down to here. I throw in an enzyme, I throw in a catalyst, which could be an enzyme, but in this case it's not, and it lowers it. So now I only have to go to this peak here relative to that peak. That's a significant amount of energy less, which therefore speeds up the reaction. More of it happens, more product forms. And that's what a catalyst does, literally, for the most part. Anybody unclear on that? Any questions on it?
Well, it would be the same amount of product, but at a slower time, at a faster time. I mean,
Would it be the same amount of product?
Energy.
It depends how much reactant you have. If you have a limited amount of reactant, it would be. If you have unlimited reactant, then,
that would be right.
right, it would be more more product would form.
On a time.
You have unlimited, well, let's just say, we hope there's unlimited O3, right? At the rate it's degrading, which is protecting us from what? The UV light.
Exactly.
Right.
Yeah.
So let's put that in perspective, right? So there's plenty of this,
Ozone, right? Ozone.
right now at least. Well, there's a lot less than there used to be, but there's still plenty of it in this conversation. Maybe less than we probably want in general as human beings, right? Okay, so is this, any other questions on this? This one okay? So I think one question is like, why double hump here as opposed to single there?
Right.
Right, that should be an obvious question. And it's a different number of,
2 steps or
yeah,
something.
different steps that are being involved in it, absolutely. Right, so each one has its own side. I mean, it's just not just a straight here curve. You have to overcome the first transition state and then the next one. In other words, just as it says, there are multiple transition states, hence different reactions. Okay. So those are Cl atoms that are doing this. These are really just CFCs, right? And usually it's something like CCl2, F2 are the more common chlorofluorocarbons, which is what a CFC is. And then the chlorines are able to dissociate, and then they speed up the reaction of the O3 degradation at the level of the rate limiting step. That's all that's happening. Go ahead.
And they're not being consumed in the reaction at all, right?
They end up reforming Cl2s, if I recall the mechanism. I think they come off the CCl2F2 in general. There are other types of chlorofluorocarbons, but it's usually CCl2F2, and the one Cl comes off as a radical, if I recall. It's going way back from my memory. That one Cl then, of course, is going to bind to the radical O and carry another. Then another one comes off, and it carries those. They form, and then they form as a Cl2O2, and then the O2 comes off of that, forming another Cl2. And so that's the speeding up of the O2 formation.
Would that hump also?
Which is not good, right? Because if you look at that first reaction, if you pull away those individual oxygens, then now they cannot go backwards to the O3. Do you see why that matters? Maybe I should, that's actually a really interesting point. Even though I'm getting a little further behind, I think putting these things in perspective makes it not only easier for you guys when you're studying, but also puts it in some, realistic environmental scenario that we're living. So you have, remember, this goes O3, breaks down into O2 plus O, and I'm going to put the radical there, and then I end up with the O radical plus O3 forming the O2, right? And there's two of those. That's what it was. So this is the rate limiting step, right? So now I have a CL, a CCl2F2. This is a CFC. And this goes through some with UV light, by the way. It's just the light, the energy coming from that gives me ClF2, and then you get the Cl radical coming off of it. This thing now can bind to this, remember that's the, and now it pulls that away.
Then you only get.
So then it does this and it forms Cl2O2, and then this releases the O2. So you're pulling this out. Now the relevance of that is this. As I pull more of this out, then I also shift this equilibrium this way, forming more of that, not allowing more to go back as O3, because that's in equilibrium. That's Le Chatelier's principle. We'll get into that next chapter.
Right.
Got it.
So it does a few different things. Remember, it's a catalyst because it's speeding up the overall reaction. This is just one part of how it speeds it up, and then it also is pulling these things and converting them much faster than this is converting it. Because this is a slow rate limiting step, and this does this pretty quickly. You have a Cl and an O. They can't wait to get together because they have these unbound, unpaired, I should say, electrons, which are really, really, really active. They don't like to be in that state. Okay, so then before we go, let me get through a couple more. Anyways, that's all this is doing here. So it just lowers the activation energy. So basically, with the Cl2, I've done this to this reaction. With the CFC and the Cl radical. You don't need to know this mechanism. This is just for your own knowledge, just to have a sense of why these things matter.
So that, I guess the O2s kind of are representing that hole in the ozone layer, I guess?
Yeah.
Because there's less of the actual
Yeah.
ozone.
Mhm. Okay. As you break down and degrade the O3, you're not getting any more O3, you're losing it, and you're losing it as O2. Yes. Unfortunate, because it protects us from the light. Okay. So obviously we don't like that, so maybe we could find a way to block this, which would be to stop using them and making them, obviously. Among other things, but anyway, so that's an unfavorable speeding up of a reaction. So here's a more favorable one, something like a catalytic converter you have in your car, where it takes pollutants and it converts them into things that are not pollutant, things that we can tolerate. So it just takes like NO mixed nitrogen monoxide mixed with carbon monoxide into nitrogen and carbon dioxide. Why is carbon dioxide and carbon monoxide, why is one more dangerous or toxic than the other? Because it binds to hemoglobin. So once again, why do I say these? These are biological. That's why I like biology also as well. But I like to know it from a real practical perspective, which is chemistry, hence biochemistry, which is actually molecular biology. So this is going to bind to hemoglobin. What does hemoglobin do? What's the point of that, though? Transports oxygen to your lungs so you can breathe.
Right.
Right? So if those things are occupied with CO, not CO2, then you can't, or not O2, then you can't bring in the O2 because they're being inhibited.
Yeah.
Right.
So then you get less oxygen. And of course you get to the point where they're all being blocked and you have no oxygen intake and of course you suffocate, right?
Yep.
So these things are important to know and put them in the proper context. That's why when you want to make sure you always have an air vent or something in your garage, right? When you turn on your car, you don't want to keep producing a bunch of carbon monoxide. Okay, so anyways, it takes, inside your car you have something called a catalytic converter. It's just a catalyst, something, it's just a piece that has different things on it. We'll talk about how that functions. And it pulls these things onto it and allows them to interact and go through this right here. So it speeds up that reaction. So that these are not released, these are released from your exhaust pipe. So it's a practical way of understanding how things work and then finding ways to improve things or make things safe or whatever else.
Right.
We have to what time do we go to?
25?
25.
Go
So
ahead.
that's why when they do a smog check, they're checking for
Yeah, for the,
Amount of.
N2 and then.
I've never actually done one, but I'm assuming they're checking for these. Yeah,
When
yeah,
you get
yeah,
the
yeah,
printout, 'cause
absolutely.
I had to
Is that what
like
it?
switch it, yeah, I had to get a new catalytic converter and I had to like get the printout and see if the
CO levels are
nitrogen
higher,
went
lower?
down,
Yeah.
the CO2 went
There you go.
down. And
Absolutely.
They actually
Oh,
have
the
those
other
on
one.
Yeah.
there. Yeah.
Yeah.
The
Oh,
CO.
yeah.
Yeah.
They
Ones
wanna
go
make
up,
sure
others
that
go
goes
down,
up,
that's good.
and then the other ones go- Yeah.
It's gotta be a certain percentage or something, right?
Yeah.
Like, there's gotta have a certain percentage of this, hopefully it's low, and a certain percentage of this, hopefully it's high.
Yeah.
And that indicates whether or not you're creating all kinds of problems for everybody that you drive by. How much further do we have? I think we only have, okay, so we only have a few slides left.
Actually, yeah, too.
Let me, you guys seem ready to go? Hungry? Okay. Efren, you shook your head, yeah. Well, you came in late, man, what do you mean? Yeah. You've already had an extra 15 minutes, right? Okay, I'll let you guys go. Have a good weekend. I'll see you guys Tuesday, okay?